Welcome to Oscillations. Today we are going to talk about the damped-driven pendulum. So the system under consideration is a pendulum made of a mass m attached to a weightless rod. This system will move naturally under gravity in a uniform gravitational field, but we also want to subject it to a torque of magnitude n in the range of motion given here. So phi is going to be the polar angle of the usual spherical polar coordinates. And furthermore, so apart from the motion under gravity and under the driving torque, we also want to have some dissipation effects present due to a viscosity eta, so the damping constant of the medium in which the pendulum is moving. Now, the definition of a torque is the usual one in terms of the cross product between the radius of the mass and the applied force. In the case of the gravitational force acting on the pendulum, so we want to, once again, we choose the x-axis pointing down along gravity, y is going to be orthogonal to it in the plane, and z is going to point towards the viewer, following the usual right-handed screw rule convention. So we've written the force, and now we want to write the radial versor and the versor of the angle phi in terms of the x and y coordinates, and these the expressions should be the ones here. And now in terms of these, we can rewrite the we can write a torque. We can write the Newton's equation for the angular momentum of the system, and we can write the angular momentum itself according to its definition, and we can write the velocity vector down in terms of its x and y coordinates, or we can transform to polar coordinates depending on what is more suitable. In any case, once we put these things together and evaluate the equation of motion written in its vector form here, we end up with the explicit expression I have given here, where I is just the moment of inertia of the pendulum. So this is the typical pendulum equation up to this point. We are only considering motion under gravity, and as is well known, for small angular displacements, we can approximate the sine of phi entering here with the value of the angle itself, and then the problem is linearized, becoming that of a simple harmonic oscillator having a natural frequency given by the square root of the ratio between the gravitational acceleration and the length of the pendulum. Now, if we apply an external driving torque, the conditions for equilibrium are given as following. The external driving torque has to be equal with the magnitude of the gravitational torque, and the velocity, the angular velocity of the pendulum has to vanish. So we see from these conditions that there exists a critical torque, a critical driving torque, having a value given by the gravitational torque when phi is equal to pi over 2, and that critical value is the one given here, so it's just m times j times r. And if we increase the driving torque beyond this value, then it's always going to be larger than the restoring torque, leading to the pendulum rotating beyond pi over 2 and continuing to do so while the driving torque remains above the critical value. And in this case, the motion will take place at a variable angular speed omega, which is just the time derivative of phi, and this motion can persist if the driving torque is later removed. If there's also a damping force of magnitude eta times omega present. Then the equation of motion takes its most general form. So it's an equation for a damped and driven pendulum. And we can define a critical frequency in terms of the ratio of the critical value of the driving torque to the damping constant. And then if we introduce this critical frequency in the expression of the equation of motion, we can recast it into this form, which is easier to analyze. So this is an equation for the angle of the pendulum, having as parameters the resonant the frequency of free vibration of the system under the gravitational under the torque caused by gravity, the critical frequency that comes from the presence of a driving force and damping force, and the ratio between the driving torque and its critical value. So this equation will have a solution which is phi of t, which will have a very complicated time dependence generally. If a constant driving torque is applied to a resting pendulum, there results a transient regime which settles down to a dynamical steady state. What we want to do in the following is just to look very briefly at the general features of several such cases of a dynamical steady state. The first case is that of the static steady state, and it's the simplest one. It involves the driving torque having this expression. So it's the critical value times the sinus of phi. And then if we introduce this into the equation of motion, we just end up with the simplified form here. So we see that the time derivatives vanish after the initial oscillations die out. And so the pendulum stays at rest at the angle phi. So this is largely a trivial case once the transients vanish. The second case involves removing the dissipation from the equation of motion, which leads to the expression here. And then we can see if we look at how the value of the driving torque changes throughout a cycle. So for various values of phi as the pendulum rotates, we see that the value tends to fluctuate with a plus or minus the critical torque around the initial value of the driving force. So we see that if the driving torque is greater than the critical value, the motion is one of continuously accelerated rotation, the pendulum increasing its energy over time. And omega will increase, but it will also fluctuate over every cycle, with its average value being just the average value of the time derivative of the polar angle. The third case is that a quasi-static motion, which happens when damping is present, but the critical frequency is much smaller than the resonant frequency, and the driving torque is much greater than the critical value. So what happens then is that omega will increase until the damping term approaches the applied torque. Then the average of omega will approach its limiting value, which I've written in brackets, and the acceleration fluctuates around a null average. So neglecting the acceleration term in 692, we arrive at the equation of motion here, which has an analytical solution. So we can rewrite it first of all we can rewrite it in this way, and with omega being given by the time derivative of phi, and then if we try to integrate it, to integrate it with respect to phi and time, we can use first of all the change of variables here, given by the variable u being equal with the tangent of phi over 2, and then also changing to the variable v defined by the relation here, to the goal being to transform the integral in each step and to bring it to the form here. The reason why we want to do it in this way is because integrals of this form are known. They are of this type, so they can be solved in terms of the arctangent of the ratio between the variable x and the parameter a. So really what we have obtained for this particular equation of motion is the following set of results. The average of omega will vanish if the driving torque is smaller than the critical value. This is seen straight away. Then by virtue of this result, the average is generally going to have this expression when the driving torque is greater than the critical value, and if it happens to be much greater, then we can approximate this once again by essentially by neglecting 1 in the square root, and we find this value of the average frequency of the motion. So in this particular case, the frequency tends to behave almost sinusoidally for this particular situation. And the last two cases, for the last two cases, the fourth one involves a vanishing dissipation and a critical frequency that is far greater than the natural frequency of the pendulum, and the result 698A is still going to apply when the driving torque is smaller than the critical value, and with the pendulum fixed at the angle defined by equation 693. So by the condition of the static steady state. So this will imply that the frequency of the motion and its average vanish. 698C, so the result here, is still going to hold for all values of the driving torque. So we have these two cases. Omega is 0 with the driving torque is smaller than the critical value, but also the average of omega is equal to the result here for an arbitrary positive torque. So what we are seeing is the phenomenon of hysteresis. So the behavior of the system being different whether the torque is increasing or decreasing. So if the torque increases while its value is below the critical torque, the pendulum stabilizes at the angle phi for which omega vanishes. Then when the driving torque reaches the critical value, omega will jump to the critical frequency, and then it will rise linearly with the driving torque. For decreasing values, the average of omega will remain proportional to n all the way to the origin. And finally, the last case, so the one in which the critical frequency is very close to the natural frequency of oscillation, requires a full numerical investigation of the equation 692, as no approximations can be made, as was the case in the other situations that we have studied. The reason why the damped-driven pendulum is interesting is because it finds applications in a domain that is quite far away from classical mechanics, namely in condensed matter physics. In the particular problem of the Josephson junctions. So a Josephson junction is consists of two superconductors that are separated by a thin insulating layer. And its most interesting property is that an electrical current I can flow across the junction with zero applied voltage up to a certain critical value. And beyond this value, the current is accompanied by the presence of a voltage, and the current voltage plot for the junction exhibits hysteresis. And what's interesting is that the same equation of motion 692 that we have studied here applies in this situation with by making the following transformations. So if we associate the current with the driving torque of the pendulum, the voltage with the angular velocity of the pendulum, the capacitance with the moment of inertia, the conductance with the viscosity, and the angle of the pendulum with the phase of the current. So I should have placed these the other way around. So it's the phase of the current which takes the place of the angle of the pendulum. So with these associations we can write the equation of motion for the Josephson junction analogously to the equation for the damped driven pendulum. So it has the same structure, but then the physical quantities in the case of the junction correspond to the mechanical ones for the pendulum for this for these relations. So in summary, we have described the damped driven pendulum, derived its equation of motion, and studied various dynamical steady state regimes. We've mentioned briefly Josephson junctions and established that the damped driven pendulum is their mechanical analog. Now, as an overview of the entirety of the discussions up to this point, we began everything with a survey of Newtonian mechanics, and then we have formulated Lagrangian mechanics in two ways, through the local D'Alembert's principle and through the integral Hamilton's principle. And the reason we did this wasn't necessarily to discover new physics, but rather to put Newtonian mechanics in a framework that made it more powerful and more suitable for diverse physical applications. Essentially, we just wanted to write the theory in a way which makes it easier to solve actual problems and to study physical phenomena. And as applications of Lagrangian mechanics, we have covered the following broad topics. So we have looked at the central force problem, and we have mainly studied Newtonian gravity and Coulomb scattering. We have looked at motion in non-inertial frames of reference, and particularly we have studied the Coriolis effect. We have looked in great detail at rigid body dynamics, with particular examples such as the heavy symmetrical top in a uniform gravitational field, the precession of the equinoxes, the Larmor precession in the magnetic field, and we have also talked about small oscillations around equilibrium positions, where the most important physical systems under study were linear triatomic molecules, and we have also looked at the situations involving damped and driven oscillations. In the following, we are going to change the paradigm slightly, and we are going to look at the modifications that are required in order to make Newtonian mechanics compatible with electromagnetic theory and electrodynamics. So we are going to study the modifications of classical mechanics that take place within the theory of relativity. Particularly right now we are going to talk about the special theory of relativity. I might mention very, very shortly and just in very broad terms the principal ideas behind the general theory of relativity, but general relativity is a topic that I will want to address later in a separate discussion. So for now we can look forward to the special theory. That being said, I want to thank you very much for watching. I hope you found the discussion worth your time, and I will catch you later. Goodbye.